Capacitance and capacitors. The simplest version of a capacitor is the parallel plate capacitor, which consists of two metal plates that are parallel to one another and located a small distance apart. As before, the plates here are shown very far apart compared to real capacitors for clarity. When a battery is connected to the plates, charge moves between them. Every electron that moves to the negative plate leaves a positive ion behind. The plates have equal magnitudes of charge, but one is positive, the other negative. The electrons in this positive plate up here are attracted to the positive terminal of the battery, and they move through the wire and through the battery to arrive on the other plate. Only unpaired protons and electrons are represented here. Most of the atoms are neutral, since they have equal numbers of protons and electrons. The electric field is uniform everywhere in a capacitor's gap. It has the same magnitude and direction. In this case, the electric field points straight down. Also, there's no field outside the gap, so there's no field outside the capacitor. The parallel plates of the capacitor have a finite size, but they're designed so that the plate size is much greater than the distance between them. So the capacitor properties are very close to the infinite plane case. The charge separation for the plates is caused by the battery. The battery does work on the charges in order to separate them, which increases the potential energy of the system. The electric potential energy is stored in the electric field that is created. A capacitor can store a certain amount of charge for a given voltage. That is called its capacitance, C. Capacitance is determined by the physical characteristics of the capacitor. By definition, delta V, the voltage difference, equals charge divided by capacitance. The voltage difference between the plates is equal to the amount of charge stored divided by the capacitance. This equation is true for all capacitors, not just parallel plate capacitors. The unit of capacitance is the farad. A farad is a coulomb per volt as indicated by the above equation. If we solve this equation for C, C equals Q over delta V. Now Q is charge in coulombs, V is voltage in volts, so we get coulombs per volt. A farad is very large, so we're going to use these names for smaller capacitances. Picofarads, nanofarads, microfarads, and millifarads. The area of the capacitor is the surface area of one plate and is represented by the letter A, capital A. The distance between the plates is represented by the letter D, lowercase d. Both plates have the same surface area, A. For parallel plate capacitors, capacitance increases with the area of the plates and decreases as the plates get farther apart. So capacitance is directly proportional to area, and capacitance is inversely proportional to the distance between the plates. So combining these two relationships, we get this. When an equation has a proportion sign, it can be replaced by an equal sign and a constant, the constant of proportionality. For capacitors, it has been theoretically predicted and experimentally measured and verified that the constant of proportionality for the equation is the permittivity of free space, epsilon naught, which is a small number, 8.85 times 10 to the negative 12th coulombs squared per Newton square meter. The permittivity of free space is a physical constant that reflects the ability of electrical fields to be created in a vacuum. So, for parallel plate capacitors, this proportionality becomes an equation as soon as we put epsilon naught in it. The larger the area, the greater the capacitance, as there's more room to store charges. The closer the plates get to each other, so D decreases, the higher the capacitance. Example 1. Which capacitor can store more charge? Here we have C1, capacitor 1 has an area A and a distance between the plates of D. Over here we have an area of 2A and the separation of the plates is 1/2 D. Alright, so we're going to use our equation. For capacitor 1 we have a capacitance of epsilon naught A over D. For capacitor 2 we have 2A and 1/2 D. And when we do the algebra, this 1/2 flips up to the top, and we get 4 epsilon naught A over D, which is what we started with C1, right? So capacitor 2 can hold 4 times the amount of charge as capacitor 1. Imagine you have a fully charged capacitor. If you disconnect the battery and then change either the area of the plates or the distance between the plates, what do you know about the charge on the capacitor? Think about the conservation of charge and how charges flow before going to the next slide for the answer. The charge on each plate will remain the same since there's nowhere for it to go. Charge needs to flow through a conductor, and once you've disconnected the battery, there's no path for the charges to flow through. So the charge on the plates will remain constant. The conservation of charge, the charge you start with, is equal to the final charge. And this is why you should never handle a capacitor if you don't know where it's been. It might be holding a charge that would then go through your body to the ground, which can be very dangerous. Now let's imagine another scenario. You have a fully charged capacitor. We're going to keep the battery connected, but then we're going to change something about the physical characteristics of the capacitor. We're either going to change the area of the plates or the distance between the plates. What do you know about the voltage across the plates? Before going to the next slide, think of conservation of energy. The voltage will remain the same. Voltage is the amount of energy delivered to each charge as it passes through the battery. Energy is conserved regardless of the capacitor's physical configuration. The energy stays the same, hence the voltage stays the same. However, the capacitance of the capacitor has changed, and therefore the amount of charge stored on each plate will change. Think of batteries as a source of constant voltage difference. As long as you have a battery connected to a capacitor, that voltage difference between the plates will be constant. After being fully charged, there is a potential difference, delta V, between the two plates. The voltage difference is equal to the voltage supplied by the battery. There is a uniform electric field, E, between the plates. We learned earlier that with a uniform electric field, the strength of that electric field equals the voltage difference divided by the separation of the plates. This is true in the case of the parallel plate capacitor. The electric field is constant everywhere in the gap between the plates. The electric potential, or voltage, declines uniformly from the top plate to the bottom plate, from, let's say in this case, plus V, and then 1/4 of the way down, we would be at 3/4 V. Halfway, we are going to be halfway between the plates. All the way at the bottom plate, we're going to have 0 voltage. The equipotential lines are shown in green. They're always perpendicular to the electric field, as they were before. A good way to visualize this is imagine the top plate being the top of a hill, and then the negative plate is the bottom of the hill. So if you placed a positive charge here, it would roll downhill to the negative plate. Now, just because the positive plate is on top here, doesn't mean that you can't have a capacitor with positive charges on the bottom and negative charges on top, in which case this would be the top of the hill, and then positive charges would roll down the hill towards the negative plate. Why are we showing 0 voltage for the negative plate? Shouldn't this plate have negative voltage? Well, it's somewhat arbitrary. The important fact is that delta V is going to be the difference in voltage between the top and the bottom. We could easily have also done this. We could have said this was V over 2, that's negative V over 2, and therefore it's 0 in the middle. That would have also worked. But people like positive numbers more than negative numbers, and really it's just the difference between these values that's important to us.